thank you and thank for all the organizers for the invitation, and thanks everyone for coming. So today I will be talking about how we can use Markov chain Monte Carlo methods for both sampling and theoretically analyzing certain ranking models. And the particular Markov chain Monte Carlo methods that I'm going to talk about is called the hit and run algorithm. So here is a brief outline of the talk today. So I will start by introducing the ranking model that we will be focusing on today. It's called the Mallows permutation model. So this model actually has quite a bit of history. It was introduced by C.L. Mallows first in 1957, so that's quite a long time from now. And recently, there has been a lot of ranking data involved. I'm going to show a few slides about such examples. So ranking data are quite popular in a lot of applied fields, such as electronic commerce and voting systems and various others. And the Mallows permutation model is a very useful model for analyzing such ranking data. So I'll start with an introduction to this Mallows permutation model. However, for the model that we are going to consider, there is a difficulty that is commonly faced by Monte Carlo researchers. That is, the ranking model that we are going to consider has a normalizing constant that is intractable. And therefore, we have to develop some Markov chain Monte Carlo algorithms. And we are going to use the so-called hit and run algorithm. I'll give an introduction in this second part that can be used to efficiently draw samples from the ranking models that we consider. And then we are going to show that those hit and run algorithms have theoretical guarantees and are efficient. So it will mix very fast. And so those are the second and third points here are more about sampling aspects. And I will also talk about another use of hit and run, says that hit and run is not only useful for drawing samples from this model, but it can also help us as a mathematical or theoretical tool for analyzing certain properties of the ranking model that we consider. And I'm going to end in the end, I'm also going to talk about some future directions. Okay, so let me start with ranking data and the ranking model that we consider. So with the advent of big data, so we have a lot of data available to us, and especially with the advent of large language models, we need to analyze all those complicated data. And ranking data are quite ubiquitous nowadays. So I have listed a couple of examples here. So here in panel A, it's about ranking data has been used a lot in recommender systems. So in recommender systems, it is a system that wants to give personalized recommendations of items to particular users. So there can be a lot of users. Each user can have her or his own preferences. And so recommender system would provide a list such that the user can see whether the user wants to purchase or not. So this would involve a ranking of different items for each particular user. Here I have listed some items which may be of interest to user, and it is important in developing recommender systems to come up with a ranking of the items according to the preference of the user, so that it would be more efficient in advertising those items. And ranking data also comes up a lot in market research. Here is an example regarding ice creams. So there are different flavors, and in market research, we want to come up with a reasonable list of rankings of different ice cream flavors that reflects the preference of the customer population. And ranking data are also used a lot for example, in search engines. In each search engine, when we search certain items, we want to have, it will give us a list of web pages that could be relevant. So ranking web pages according to the relevance of that web page with the keywords that we input is important. And lastly, ranking is also used in electoral systems because, so this is an example of a voting system where each where each voter needs to rank the different candidates for a certain job. So we can see that ranking data are quite ubiquitous nowadays. And in order to model ranking data, we typically use language permutations. So here is an abstract setup for ranking data. So suppose we have a list of n items labeled by 1 to up to n. We typically encode a ranking of those items, ranking them from the top to bottom by a permutation sigma. So I'm going to call Sn the set of permutations, one to one permutations of those 1 to up to n. So a permutation is just an injection from this set to itself. And a ranking of the n items can be specified by a permutation sigma in Sn, so that sigma I would represent the rank of item I. So the ranks would be from 1 to up to n, and this allows us to give a ranking of the different n items. Okay, so if we want to use a ranking model to model a particular to model certain ranking data, we can just one way is to use probabilistic modeling, that is to model the data as being generated from certain underlying distributions on those rankings. And we are going to, in this talk, we are going to consider the so-called Mallows permutation model, which specifies certain probability distributions on ranking data. Okay, so here is a brief introduction to Mallows permutation model. So it is first introduced by C.L. Mallows in this classical paper. And roughly speaking, Mallows permutation model specifies a class of non-uniform probability distributions on Sn, whose specific form I will introduce in the next slide. So since its introduction by Mallows, this model has been widely used in both statistics and machine learning and other fields, including psychology and network analysis. So some references are given out here for the application of Mallows model for ranking data in those different contexts. Okay, so now let me introduce the specific form of Mallows permutation model. So the model actually involves quite a few model parameters. So the most important one is to specify a particular Mallows permutation model. We need to specify a certain distance metric on the set of permutations. So I'm going to call this distance metric d of sigma and tau. So sigma and tau are both permutations of 1 to up to n. And this distance metric give a way to measure the closeness between two permutations. So since the space of permutations is a discrete space and involves a lot of so for example, permutations of order n of 1 to up to n has n factorial elements, and so we need some care in designing those distance metrics. I'm going to show several examples of such distance metrics in the next slide. And besides the metric, we also need to specify a scale parameter called beta, which is a real value, and also a location parameter sigma 0, which is a permutation of 1 to up to n. We are going to think of this location parameter sigma 0 as a central permutation, such that draws from the Mallows permutation model are going to cluster around this location parameter. Okay, so those are the model parameters. And given those model parameters under the Mallows permutation model, the probability of picking a certain ranking sigma, which is a permutation of 1 to up to n, would be specified by this exponential family. It's proportional to e to the power of minus beta times the distance. So d is this distance metric that we specify beforehand, times the distance between sigma and sigma 0, the central permutation. And therefore, we can see that, so typically for usual distance metrics, if beta is a positive number, then once the distance between sigma and sigma 0 increases, the probability would decay exponentially. So a typical draw from this Mallows permutation model would be clustered around sigma 0. But since we have noises, it would not exactly be equal to sigma 0. Okay, and for convenience, In this talk, we are going to focus on the regime where beta is positive. So this will make the model to be centered around sigma 0. And we are going to assume that the central permutation sigma 0 is just the identity permutation. However, I want to comment that the hit and run algorithms that we develop also works for general scenarios, even if we are considering general real values of beta and a general central permutation sigma 0, the hit and run algorithm still applies. Okay, so here comes a list of common distance metrics used in statistics and machine learning. So the first two examples are the ones that I'm going to focus on in this talk. They are called L1 distance or L2 distance. So these distances are also referred to as Spearman's footrule and Spearman's rank correlation in statistics, psychology, and machine learning literature. And besides those, there are also two other distance metrics that are commonly used called Kendall's tau and Cayley distance. However, since they are not the focus of this talk, I'm not going to introduce the specific form for those two other choices of distance metrics. And I will just introduce the concrete formula for computing L1 and L2 distances. So just as the name suggests, so if we have two permutations, sigma and tau, recall that they are bijections, so they are functions from 1 to up to n to itself. So the L1 distance between two permutations, sigma and tau, are defined as the sum of I from 1 up to n times the absolute difference between sigma I and tau I. So this can be viewed as writing sigma and tau in the form of two n-dimensional vectors. So the first vector would be sigma 1 up to sigma n, and the second vector would be tau 1 up to tau n. And if you consider the L1 distance between the two vectors, you get exactly this form. And if we replace the L1 norm by the L2 norm squared of between the two vectors, we get the L2 distance, which is written in this form. So one caveat here is that for L2 distance, we are not considering the square root of this thing, following the convention in statistics and psychology. Okay, so with those introduced distances, we are going to focus on Mallows permutation models with D given by those specific forms. However, those Mallows permutation model has computational challenges, and the main one is that the normalizing constant for both of the models. So this is for the L1 model, and this is for L2 model. Those summations can be written in terms of certain permanence. However, for those permanents, there is no general. So unlike determinants, computing the permanence in general can be hard. And for those two specific forms of permanence, we don't have a good explicit expression for computing them exactly. And even approximately computing up to some errors can be difficult. And besides the intractability of the normalizing constants, there is also no non-efficient exact sampling algorithms. Here, by exact sampling algorithm, I mean a way to draw samples from either of the two models, such that the distribution of the draw follows exactly from the model. So there is no such algorithms, which will also cause difficulty in sampling from those models. And due to those aspects, both sampling and analyzing Mallows permutation model with those distance metrics can be challenging. Okay, and in this talk, we are going to talk about, introduce a so-called hit and run algorithm, which is a family of Markov chain Monte Carlo algorithms that can help us achieve both goals. So we can first based on those hit and run algorithm, we can efficiently draw approximate samples, which are permutations following approximately the law of Mallows permutation models from both of those Mallows models. And we can also, besides that, we can also analyze the properties of those Mallows models. Since those are models of permutations, typically we want to think about, for example, suppose we consider one feature or statistic of the permutation that is drawn from the model, such as the longest increasing subsequence or the number of fixed points. And we may want to understand its probability distribution because those are useful for constructing, for example, test statistics or estimates in statistical inference and estimation for those permutation models. And we are going to see that the hit and run algorithm that we introduce, besides being useful for sampling, can also be used to analyze the distribution of such statistics. Okay, and so here are a few applications of being able to applications of these approximate sampling methods. So first of all, is those generated permutation samples can be used for visualization, because if we want to understand the probability distribution of the number of fixed points of the permutation from the model, we can just draw samples and compute the fixed number of fixed points and draw a histogram. And besides that, it can also be used for statistical estimation and inference. So in this context, we can consider the scenario where we observe a bunch of permutation samples. So maybe which could consist of sigma 1, sigma 2 up to sigma capital N, which are rankings given by different users. And if we want to infer the parameter, say beta, suppose that we fix a particular sigma 0, the central permutation, and we want to estimate or perform inference on the scale parameter beta, with the help of those hit and run algorithms, we can use Monte Carlo maximum likelihood estimation introduced by Geyer to perform such estimation and inference tasks. Since, as we are going to see later, that we have mixing time guarantees for those hit and run algorithms, this would also allow us to have statistical guarantee on the application of Monte Carlo MLE in this context. Okay, so those are the context, and now I'm going to introduce the hit and run algorithm and see how they can be used to generate samples from those Mallows permutation models. So hit and run algorithm itself is a pretty broad class of Markov-Chain Monte Carlo algorithms, and here is a comprehensive survey. And important examples of the hit and run algorithm include the Swenderson-Wen algorithm, which is an algorithm for sampling from both the Ising and Potts models, which is a model that for modeling ferromagnetism and has also been used in social network modeling. Besides Swenderson-Wen, the hit and run algorithm class also includes the data augmentation algorithm, which is used a lot in Bayesian computation, because in Bayesian statistics, we typically want to approximate the posterior distribution, and the data augmentation algorithm is typically efficient for sampling from those posteriors. Okay, so hit and run algorithm is one class of Markov-Chain Monte Carlo, and in Markov-Chain Monte Carlo, we want to sample from some probability distribution by designing a Markov chain whose stationary distribution matches our target. And if we run the Markov chain for long enough, the distribution would be close to the stationarity. And of course, we also need to see how long would it be enough for getting a sample that is close to the stationarity, which involves a mixing time. Okay, so now I will introduce the hit and run algorithm. So the classical or original version of the hit and run algorithm involves sampling from a probability density on d-dimensional Euclidean space. So it involves the following two steps. So since it's a Markov chain, we start from some point in the d-dimensional space, call it x. And the first step involves selecting a point that's uniformly at random on the unit sphere that's centered at x. So here is a two-dimensional example. We start from x and consider the unit sphere around x, and we just draw a point uniformly on this sphere. So this would determine a line that connects x and y. And the second step of hit and run is to pick a point z on the line that's determined by x and y, and the distribution of this point z follows from the conditional density of the original density when restricted to this particular line. So that's why we call it hit and run algorithm, because we start from x, we hit a point on the unit sphere, and then we run along this line. So this is the original version. And in the paper that I mentioned earlier by Diaconis and Anderson, they introduced a general framework that gives a general version of the hit and run algorithm to allow it to incorporate a lot of known Markov chain Monte Carlo algorithms. So I'm going to talk about this general algorithm in the context of sampling from a probability distribution pi x on a finite or countable state space, call it script of x. So this is just for convenience of notations. It also allows a generalization to general continuous spaces. Okay, so to introduce this general hit and run algorithm, we need to specify several ingredients. So the first ingredient is a finite set I. So those I will serve as the analog of the lines. So in the previous example, it's a line determined by x and y. So in the first step of the original hit and run algorithm, we pick a point uniformly on the sphere, which is equivalent to pick a line that passes through x. So this finite set I would serve as analogs of possible lines that we can pick. Okay, and after specifying this set I, we are going to introduce a proposal kernel, which is roughly speaking a probability distribution that depends on x. So roughly speaking, this proposal kernel specifies a probability of how we can jump from x to I. So suppose we start from x, then we want to pick an element from this capital I, the analog of the lines, and this choice is specified by this Wx of I, where Wxi is a probability of choosing I if we start from x. Okay, and once we have fixed this proposal kernel, we can obtain a joint probability distribution in this form. So since here pi x is our target distribution that we want to sample from, we just multiply the target by the proposal kernel. And so this would involve both x and I, and it can be checked that it's a probability measure on the product space of x times I. Okay, and so this is a joint distribution, and we can compute. So since now we have already jumped from x to I, we can compute the conditional distribution of x given I, given the current line I. And hit and run algorithm also require us to specify a Markov chain, which can depend on I, the current line of jumping from x to y. Okay, so those are the quantities that we need to specify to design a hit and run algorithm. And once we have those ingredients, we can just run the algorithm based on the following two steps. So the hit and run algorithm would jump alternatively between x and I. So we start from some element x in the set x, then we choose a line little I from the finite set capital I, following the proposal kernel. So we jump from x to some I, and once we have jumped to I, this will determine a conditional probability that depends on I, and we have already specified a Markov chain based on I, and then we run one step of the Markov chain from x to y. So x is the starting value, and once we have taken this step, the y would be the new sample, and we jump from I to y, and then we can iterate. So we can see that we have this kind of alternating structure from x to I, and then go back to x and then I. And it can be checked that even under this general setup, the stationary distribution of a Markov chain thus designed is exactly given by the target distribution pi of x. And as has been observed a lot in practice, this kind of hit and run Markov chain, since we alternate between x and I, it can typically make big jumps in the original space x, because we have already taken I and then go to another y. It will typically make y and x very different, and it has observed to mix much more rapidly than local algorithms such as Metropolis-Hastings algorithms empirically. However, establishing mixing time guarantees for this kind of general version of hit and run algorithm still remains a challenge. Okay, and now I want to talk about how we can specialize this kind of hit and run algorithm to sample from both our Mallows models. I will start from the L2 model, the Mallows model with the L2 distance. So in Mallows model with the L2 distance, we notice that we can first thing to notice is that we can rewrite the L2 distance. Recall that the L2 distance between sigma and sigma 0, which for us now is the identity permutation, is in this form. So if we expand the squares, we get this thing. And one thing to note is that the summation from I from 1 up to n of the first term, sigma I squared, is exactly equal to the summation of I squared, because sigma is a permutation. So sigma 1 up to sigma n would just be a permutation of 1 to up to n. And that gives us this form. And the trick here is to note that the first term doesn't depend on sigma. So we can equivalently write the probability measure for the L2 model in this form. So originally it's e to the minus beta times this quantity. And since this term doesn't matter, we get this new form of probability distribution. And the motivation for doing this kind of transformation is that, as we will see later, if we specialize hit and run algorithm to the L2 model, if we use this form, the second step will be easy to sample. If we don't do this kind of transformation, the second step would actually be hard to sample. So those involves the concrete algorithm here. So now I want to specify the ingredients in order to apply hit and run algorithm to sample from those L2 models. So first of all, we need to introduce a finite set I, which specifies a set of lines. So in the current setup, we are going to consider the set of I to be n non-negative real values. So u1, u2 up to un, each of them are required to be non-negative values. So the set of I would be equal to 0 to infinity to the power of n in this context. And we can also specify a proposal kernel, which specifies, suppose we start from some permutation sigma. So the space of permutation plays a role of script of x in the general algorithm description. And we need to specify a way to jump from x to I. The I is specified here. So given a permutation sigma, we want to see what kind of u, which involve u1 up to un, should we draw. And we are going to choose the proposal kernel to be the uniform distribution on this space. So this basically says that for each coordinate 1 to up to n, we are going to sample ui from the uniform distribution on the interval from 0 to e to the power of 2 beta I sigma I. Okay, and this would yield a joint distribution f sigma u obtained by multiplying the target distribution. For us now is the earlier distribution of Mallows. So is the earlier distribution we have specified here. We are multiplying this quantity with the joint distribution of the proposal kernel, and it can be checked that things will cancel out, and we are actually getting a uniform distribution on the pair sigma and u, where sigma is a permutation of 1 to up to n, and u is an element falling inside the interval. Okay, so once we have determined the joint distribution, we only need to specify a Markov chain that depends on the line. The line here is u, so it's a Markov chain depending on u, and it must specify a way to jump from sigma to a new permutation tau. So here, since the joint distribution is easy to obtain, we can also see that the conditional distribution of sigma given u is also easy to describe. And we are going to specify a trivial Markov chain. That is, we directly sample from the target conditional distribution. This is also a valid Markov chain for sampling from this distribution. And the conditional distribution would just be the uniform distribution on the set of permutations that satisfy this constraint, as can be seen from this joint measure. Okay, so those are the ingredients for specifying a hit and run algorithm for the L2 model. And here it would be a description based on those specifications. So from any permutation sigma, we need to choose an element of the set I. So here we need to choose u1 up to un. And as described before, the proposal requires us to choose ui independently from the uniform distribution on this interval. So this would give us a way to jump from sigma to u1 up to un. And in the second substep, given U1 up to Un, we need to choose a new permutation tau, which is uniformly from this set. And it can be checked that in order for tau to satisfy this constraint, it's equivalent to require that each coordinate or rank specified by tau is at least some value, bi, where bi can be computed based on ui as here. So once we have determined the u's, u1 up to un, we can compute b1 up to bn. And the second step would involve drawing a permutation uniformly from this set of permutations with a one-sided restriction. So here we call it one-sided restriction because we require each coordinate to be at least some quantity. If we require all the coordinates to be less than or equal to a certain quantity, it's also a one-sided restriction. Okay, so we can see that here the first step is easy to run. It's just drawing n uniform random variables. And it can be checked that here for the second step, we can also efficiently implement a sampling procedure from those kind of permutations with one-sided restrictions. And as commented before, this is actually the reason why we want to transform the original probability distribution into the form of e to the power of 2 beta times the sum of I sigma I. Because otherwise, we are going to get, if we don't do this transformation, we are going to get some set of permutation that's more complicated and is not easy to sample from. Okay, so here is an example of permutations with one-sided restrictions. So basically, we require that each of tau I to be at least a certain quantity. And here we have placed some restrictions, and this gives a valid specification of the set of permutations with these kind of restrictions. So here the orange line specifies set. So the horizontal coordinates gives tau I, and the vertical coordinates gives I. So to specify a permutation, we need to specify for each of the rows, we need to specify what which column should we put the tau I values. And here the orange lines gives a one-sided restriction saying that, for example, tau n here must be at least be of this value. So only this block is allowed. And here it says that tau 3 must be at least this value. So only 2, 3 up to n are allowed. And this specification, those orange dots gives a specification of a permutation that satisfies this constraint. And so we can see there are a lot of permutations that could satisfy those constraints. And in order to sample uniformly from those sets, there is actually a nice sequential implementation that would only involve n sampling steps in order to sequentially determine the coordinates of tau. Okay, so here I have listed the sequential implementation in order to sample uniformly from this set. So once we have determined the u's, u1 up to un, we can compute b1 up to bn. And in order to draw a uniform permutation from this set, we start by looking at places j, where j is 1 to up to n, such that the bj coordinate is less than or equal to 1. So there are sometimes there are only a subset of j's such that bj satisfies this constraint. So this would give us a bunch of j values. And we are going to place the symbol 1 at a uniform choice among those j's. So this means that we pick some j uniformly at random from available locations, and we are going to specify tau j be equal to 1. And similarly, after we have determined this place j for the symbol 1, then we look at the remaining places j. So we have deleted this j and look at the remaining coordinates j's such that bj are less than or equal to 2. So this would relax the constraint, and sometimes so new j's would be entering the available locations, but also we also need to delete the previous selected j from the available location. And we pick another j uniformly at random from those available locations and specify tau j to be equal to 2. And we can just continue, and you can see we can see that once we run those kind of sequential steps for n times, we would sequentially determine which j would be mapped by tau to 1, 2, up to n. So this would uniquely determine a permutation. So that's how we can draw tau from this set. And it can be checked that the tau generated, implemented in this way, follows exactly the uniform distribution on this restricted set of permutations. Okay, and here is a concrete example. So if beta is equal to 0.5 and n is equal to 3, suppose that this is the current permutation. This means that sigma 1 is 2, sigma 2 is 3, sigma 3 is 1. So we can, so based on this current permutation, we can determine the endpoints of the interval for drawing UIs. So the endpoints are listed here, and we draw each of UI from the uniform distribution on 0 to the right endpoint, and suppose that UI are drawn as this. And we can compute BI based on the earlier formula. And our task for now is to pick a permutation tau at random such that each of tau I is greater than or equal to BI. And we can implement the earlier algorithm by first looking at the locations J, where Bj is less than or equal to 1. Here we can see only 1 and 3 satisfy this constraint. So only 1 and 3 are the available locations. And we are going to place symbol 1 at a uniform choice between those locations. So which is equivalent to saying that we pick one of them at random. Suppose that we pick 1 here. And then we are going to make tau 1 equal to 1. So as recorded here. And in the second step, we look at the locations J such that Bj are less than or equal to 2. So again, for now, only 1 and 3 satisfy the constraint, but we also need to delete the earlier selected location. 1 is selected earlier, so we delete 1 from the set of 1 and 3, which leaves us with the only choice of 3. So we have to place symbol 2 at place 3, which means that sigma 3 must be equal to 2, which determines this entry. And in the end, it can be checked that the only available location is 2. So we make sigma 2 be equal to 3, which gives this entry. And we can see this determines the entire permutation. And we are going to jump from the earlier permutation to this new permutation. So this is how we do the hit and run algorithm. And there is a similar hit and run algorithm developed for the L1 model. So earlier we are expanding the squares for the L2 model. However, for the L1 model, we have absolute values, so we cannot use the same trick. However, there is one thing we can notice, that is the absolute difference between sigma I and I can be written as the positive part of this difference plus the negative part of this difference, where positive part and negative part are defined here. And we can check that the summation of the positive part, subtracting the summation of the negative parts. So we can see that this is equal to the summation of sigma I minus I, because the positive part minus the negative part is just itself. And again, because sigma is a permutation, this summation is equal to 0. So the two summations here are actually equal. And therefore, we get an alternative expression for the L1 distance, which is expressed as 2 times the summation I from 1 up to n times of the positive part of sigma I minus I. Okay, so in this way, we can rewrite the original probability distribution for the L1 model in this new form. And again, we can design an efficient hit and run algorithm after this transformation. And the implementation is recorded here. It's again jumping alternatively between Sn and this U1 up to Un, where UIs are drawn from a different distribution, still uniform distribution, but with different endpoints. And the new permutation tau is now drawn from permutations with one-sided restrictions. However, this time we require tau I to be less than or equal to BI for some other formula for computing BI. So earlier we have greater than or equal to, now we have less than or equal to. However, the analog of the earlier sequential implementation still works for those kinds of restricted set of permutations. So we can still efficiently run the algorithm. Okay, so those are the hit and run algorithms, and we see that it can be efficiently implemented. And however, in order to ensure that the hit and run algorithm is indeed efficient, we need to check how long we have to run those hit and run algorithms. In particular, how would the running time depend on the size of the permutation, so that the drawn sample is actually close to our target distribution. So Those in the Markov chain Monte Carlo literature can be characterized by the total variation mixing time. Here is a definition, and I'm sure you are already familiar with those notions. Roughly speaking, the absolute total variation mixing time is determined by the minimum number of steps that we have to run the Markov chain, so that the sample drawn from the Markov chain has total variation, has distribution whose total variation distance is at the most epsilon away from the target distribution. Okay, and based on those definitions, we actually can prove that the hit and run algorithm that we have introduced mix pretty fast. So here are two parallel results. So for the L1 model, namely Mallows model with the L1 distance, if beta is within this range, I'm going to show in the next slide that this range is of practical interest. So roughly speaking, if beta is between 0 and a constant over n, then the total variation mixing time of the algorithm is upper bounded by log n. So as long as we run the algorithm for all the log n steps, we already mix pretty well. And an analog holds for the L2 model with C over n replaced by C over n squared. And in this case, we also have log n mixing time upper bound. Okay, so and here I want to say that the parameter regimes that we have shown in the mixing time results are actually of practical interest, because if we fix a constant C and if beta scales with n, so n is the size of the permutation, beta is a scale parameter, this kind of scaling, beta of order C over n, is actually of practical interest, because if we pick a permutation from the L1 model with this parameter scaling, the behavior of the permutation will be quite different from that of a uniform permutation. And a similar scaling for the L2 model is C constant over n squared. And so those are exactly covered by our two results. And so there are many aspects of the permutation drawn from each of the models that are different from uniform permutation models. And here I just want to show one example, which involves the graph representation of the permutation. So for any permutation sigma, it specifies the ranks of 1 up to n. So we can get I sigma I for each of the individuals 1 to up to n. And in the permutation literature, people usually visualize a permutation by drawing those points in the two-dimensional plane. So since each of I and sigma I are points between 0 and n, so it would lead to n points. If we plot all those points, get a scatter plot of all those points in the plane, we would get n points in this square of side length n. And in order to keep track of the patterns of those points coming from the permutation, we typically try to rescale those points since they lie in 0 to n squared. So the length of the square is growing. So in order to fix the points for different values of n on the same table, we want to rescale each of them by n. So we divide each of I sigma I by n. This would lead to n points in the unit square, 0, 1 squared. And as we increase the size of n, it would just be corresponding to more and more points in the unit square. And it is natural to ask how can we describe the distribution, specifically the empirical distribution of those points, those n points in the unit square. And for the parameter regimes that we have considered, namely beta is of order C over n for the L1 model, and beta is of order C over n squared for the L2 model, Sumit Mukherjee has shown that the empirical distribution that I have just described, basically the empirical measure of the points of those rescaled points, would converge weakly in probability to some limiting distribution with a specific density. So this would be a limiting distribution on the unit squares. And in permutation literature, people typically call this mu c a permutation limit or a permutant because it describes the limiting pattern of permutations as the size of the permutation grows. And in this work by Mukherjee, he showed that this limiting distribution is characterized by some variational formula. It maximizes certain quantity, and it can be shown that it's different from the uniform distribution on the unit square. So in contrast, if we draw a permutation from the uniform distribution on the set of on Sn, the set of all permutations of 1 to up to n, The resulting permutation limit, as described here, would be exactly the uniform distribution on 0, 1 square. So this means that if we consider the current scaling, the pattern of the points resulting out of the permutation would behave quite differently because the limiting density are already quite different. So this is one justification for why we consider this kind of scaling in our mixing time results. Okay, and one word about the proof. The proof of the mixing time results utilize both couplings for involving permutations with one-sided restrictions and also leverage that with the path coupling technique. I will not describe the details, but just to include a lemma here. This gives the required coupling for permutations with one-sided restrictions. So we are using this coupling to prove the mixing time results. Okay, and here are some empirical performance of the hit and run algorithm compared with the metropolis algorithm. So one comment I want to make is that we have proven upper bound for hit and run algorithms, and for those two Mallows models, currently there isn't any known results about the upper bound of the mixing time for the metropolis algorithm, for the corresponding metropolis algorithm, except for the n factorial upper bound, which is much larger than what we can afford. And based on simulations, it also shown that in terms of the actual running times, the hit and run algorithm also mixes much faster than the metropolis algorithm. So here is an example when n is equal to 1,000, and those are histograms for the number of fixed points. Number of fixed points of a permutation is defined as here. The histogram of the number of fixed points based on hit and run algorithm after running it for 1 step, 2 step, and 100 steps are listed as the histograms here. So we can see that after running the algorithm for 2 steps, it seems the histogram isn't too much different from running it for 100 steps. So this suggests that running hit and run for 2 steps already mixes the number of fixed points well, which takes, in practice, takes 36 times 2 milliseconds. As for the metropolis algorithm, we have listed the corresponding histograms after running it for 3,000 steps, the green one, 4,000 steps, the blue one, and for 5,000 and 10,000 steps. We can see that even after running the metropolis Hastings algorithm for 4,000 steps, leading to this blue histogram, it's still quite different from running it for even longer times. So the blue and the yellow histograms here are quite different. And running it for 4,000 steps would take around 220 milliseconds, which is much larger than 36.2 milliseconds. So in practice, we not only have a theoretical upper bound on the mixing time of hit and run, but the algorithm in practice also mixes much faster in terms of the running time. So here is another simulation. I will not talk about the details. This roughly says that for some other statistics of the permutation, say the longest increasing subsequence defined in this form, the hit and run algorithm for the statistic also mixes much faster than the metropolis algorithm. Okay, so we have seen that the hit and run algorithm is provably efficient. And moreover, there is also a weighted version weighted version of the L1 and L2 models for which we can generalize the hit and run algorithm too. So I will not talk about the details, but just to give the form of the weighted version. So if we replace sigma I and I by some weight function, say replace sigma I by W sigma I, W is a non-negative and monotone increasing function, and it replace I by Wi, then for this kind of weighted model, we can still develop an efficient hit and run algorithm, and the implementation is very similar, and we can also generalize the mixing time results to those kinds of weighted versions. Since the weighted version would introduce more flexibility, because now we can have a more complicated model involving this function W. We can use this to model more complex permutation data. And the hit and run algorithm here would again help with the maximum likelihood, the Monte Carlo maximum likelihood estimation. Okay, so those are the sampling aspects. And lastly, I would also like to comment that the hit and run algorithm that we have developed is not only useful for sampling from those Mallows permutation models, it can also be used as a theoretical tool for establishing certain probabilistic properties of the Mallows model. So, the idea is that for both of the Mallows models, we can consider permutations picked from them. And if we want to use certain features of the permutation as for use, for example, in statistical estimation and inference tasks involving the parameters, we have to understand what are the limiting distribution of those statistics that we pick. And here are a few statistics that people in working on permutations typically think of. So one feature is called band structure, which we are going to show some pictures and show some results for our models, which basically speaks of the fact that for certain parameter scaling of beta, the points in the graph of the permutations that we have just said would be clustered around a band within a band around the diagonal of the plane. I'm going to show some pictures later. And we can also consider, for example, the length of the longest increasing subsequence, which is also a typical statistic on permutations, or the number of fixed points or other structure about the cycle decomposition of the permutation. And it turns out that we can make use of the hit and run algorithm as a tool for mathematically establishing, for example, the limiting distribution of these kinds of statistics on permutations. So I'm going to present some results on the band structure for permutations drawn from the L1R, L2 models. So those are probabilistic results. And for those results, I'm going to consider a different scaling on beta. So if we take beta to be the earlier scaling, the limiting performance of the points drawn from the permutation is already shown by Sumit Mukherjee. He showed that the rescaled points would converge to some limiting distribution on the unit squares. And here, if we consider a different scaling of beta, namely, we take beta to be a larger scaling so that it's much larger than 1 over n and much smaller than 1. For the L1 model, we can observe a different performance as I will show in the next slide. Yes, so in this slide, I'm going to explain what is the band structure. So for any permutation sigma drawn from for example, I'm just going to consider the L1 model, the result generalizes to the L2 model. So if we consider a permutation sigma from Mallows model with L1 distance, we can think of its the graph associated with this permutation, and this refers to drawing the points I sigma I, basically the pair of individual I, and the associated rank sigma I in the two-dimensional plane. So if we take n to be 2000, and here sigma is a permutation that's generated using the hit and run algorithm, running it for sufficiently long time, we obtain a resulting permutation, and we can draw those points in the two-dimensional plane. And this is a visualization of the resulting graph of the permutation. So each dot here represents a point with coordinate I and sigma I. So I runs from 0, 1 to up to 2000, and sigma I also runs from 1 to up to 2000. So from this picture, we can see that most of the points drawn from this permutation model is clustered around the diagonal. So the diagonal is from 0, 0 to 2000, 2000. Most of the points seem to fall inside a band. And this is the band structure that I'm referring to. And it has also been observed from those kinds of simulations that the band width, so there is a band, so we can speak of its width. The width of the band is of order beta to the power of -1. So the red lines here, the double red lines here, correspond to plus minus beta inverse in terms of intercept. And the blue lines correspond to plus minus 4 times beta inverse. So we can see that if we take 4 times beta inverse, the band includes most of the points. And if we want to understand this kind of band structure more carefully, we might think of, suppose that we just fix a particular constant times beta inverse. What's the proportion of sigma such that it falls inside a band of order of width order s times beta inverse? And therefore, we define this statistic, which exactly gives the proportion of such points. And from this empirical simulation, we can plot this function value for different s, which gives a band of different widths. So in terms of s, we can plot this proportion in this picture. So the horizontal coordinate is s, and the vertical coordinate is a proportion of the points that fall inside this band of side lengths of width s times beta inverse. Since we know that the band has width order beta inverse, so it makes sense to vary the constant that appears before the beta inverse. And if we plot this, we get this blue dashed line. And if we compare it with e to the minus s, that's a simple function. They match surprisingly well here. Okay, and we can actually prove that. So this proof is based on using the hit and run algorithm, as I will explain the proof idea later. But our result shows that this is actually true. We can prove it mathematically. So for any fixed s, which specifies a band of width s times beta minus 1, the proportion of data points that falls falls inside this band can be described by this function. So here bs sigma is actually the point, is actually 1 minus the proportion of points for the inside of the band, because we are defining it to be greater than or equal to. And therefore, this proportion is for the inside the band would be 1 minus e to the minus s, according up to vanishing probabilities. Okay, so this gives a band structure, and based on this band structure result, we can actually show something more, such as suppose we fixed index I, so which would be an individual, as long as I lies in the bulk of 1 to up to n, so that it's sufficient away from 1 and n, we know the limiting distribution of its rank, and it's given by this Laplace distribution. So this is also how we can prove based on the hit and run algorithm. I have also included here some results about the longest increasing subsequence, which is a different statistic, but I will not talk about them in detail, but just conclude with a description of the proof ideas. Okay, so in order to obtain those results, we are making active use of the hit and run algorithm. And the idea is that, so if we sample one permutation sigma 0 from the Mallows distribution, either with L1 or L2 distance, we can just run one iteration of the hit and run algorithm, which involves certain changes of sigma 0, because we first need to draw U1 up to UN, and then have to draw a permutation with one-sided restriction implemented using the sequential procedure. So in this way, we can obtain a new permutation sigma. And since the hit and run algorithm has stationary distribution, exactly our target distribution, this new sigma is also follows our target distribution. And the benefit, so this may seems like doing nothing because we're just drawing two permutations with the same distribution. But the caveat here is that from sigma 0 to sigma, we use a hit and run algorithm, which actually brings about a lot of independent structure, because the hit and run algorithm involves drawing U1 up to UN independently, and then there is a sequential procedure, which also brings about a certain independent structure. And therefore, if we have a priori understanding on sigma 0, which we achieve by certain multi-scale analysis, I will not detail here, we can make use of the independent structure embedded in the hit and run algorithm to understand those limiting distribution of sigma. So that's the trick. So based on sigma 0, for which we first prove something, then we bootstrap the result based on running one iteration of the hit and run algorithm to bootstrap the original result, which are cruder to some more refined information about sigma. And that's how we get the limiting distribution results. Okay, so this is how we obtain a probabilistic analysis of both of the models, also through the same algorithm that we use to sample from it. And here are some future directions. For example, there are other Mallows models. So for example, Mallows model with Hamming distance or Ulam's distance and various other distances. Can we also develop hit and run algorithm for those more general models? And there are in statistics and machine learning, people can consider more complicated ranking models. For example, we can consider ranking models that also incorporate certain covariant information about either the rankers or the items. And we can also consider heterogeneous rankers. Can we also extend the hit and run algorithm to those settings? So those are the aspects that I'm lately working on. And thank you very much for coming to my talk.